Hey everyone. So in this video we will talk about Doppler effect. I will start by showing a few animations for Doppler effect, and then we will go into and work out the actual formulae that will be important for this process. So the first one that I have is over here. You can see that there is a flat plane and there is a block. Think of this red block as the source of some sort of sound. So it's emitting some sound wave, and the block itself is moving. And think about somebody standing either over here or over there and listening to that sound. So as the sound goes out in air, it radiates sort of these spherical waves. But as you see that the as the block moves forward, the person that is standing in front of the block seems to receive the same pulses that are being radiated by the block, sort of at shorter length intervals compared to a person who's standing behind over here, where clearly the wave front reaches has a larger length to cover to get to the same person. So essentially, the idea is that the wavelength of the emitted sound seems like it decreases in front of the source and it increases behind the source, right? That's the example over here. Now, this is a particular situation where the source speed is smaller than the sound speed in the particular medium that we are in. We'll consider, for our purposes, we'll consider the medium to be just air. Now, I could study the same phenomenon by making the source speed equal to the speed of sound. So in that case, something more interesting happens if I play this animation. Then you can see again the source is emitting sound, but very close to where the source is, the wavelength has pretty much disappeared, while the wavelength is much larger behind the source. All right. And we can do one more example where now the source speed is larger than the sound speed. So in that case, you will see the progressive sound waves that are emitted later on, such that the envelope of these sound wave bubbles, if we can call them so, makes the shape appears in the shape of a cone, right? And that's an example of a shock wave. It's an example that you may have heard of. So, for instance, if a jet plane goes much faster than the speed of sound, then it creates a sonic boom. So that sonic boom is an example of a shock wave. All right, so now we're gonna start moving over and starting to talk about the actual relevant formulae for Doppler effect. So this particular phenomenon, where if the source or the receiver are moving relative to each other and relative to the medium in which sound is propagating, this effect of change of frequency or wavelength is known as Doppler effect. So the particular situation that we will study is shown in this picture over here. This is a scenario where the source and the receiver are stationary. So think of this middle point over here as our source, and if a receiver is standing somewhere around on this circle, then what that receiver should actually measure as a wavelength of the sound is equal to lambda, and you all know that lambda and frequency, they're related to the wave speed. Lambda times f is equal to speed of the wave. But in this new picture, the source is now moving, and if the observer is standing over here, then the source is moving toward the observer. But if the observer is standing over here, then the source is moving away from the observer. And as you can see, if the source moves toward the observer, the new wavelength is smaller, and hence the frequency is larger, because remember, the wave speed is the same. So frequency and wavelength are inversely related to each other. And on the backside, where the observer is stationary but the source is moving away from the observer, there the wavelength increases and hence the frequency decreases. Now we're going to start talking about the relevant formulae for Doppler effect. So to start with, we will use the following notation. Lambda here will be the wavelength of sound, and this is the wavelength when everything is stationary, right? The source as well as the observer are stationary. And whenever we talk about Doppler effect in this particular video, we will consider that the medium, so in this case air for instance, is not moving. Okay, so the medium is stationary. We only consider how wavelength and frequency changes as the source or the observer start moving. All right, so as you can see, if the source were to move toward the observer, so if the observer was over here, then the wavelength decreases, and if the observer was over here behind, then the wavelength increases. And let's try to figure out how much that increase or decreases. So in order to do that, we would need to know some other interesting quantities. So for instance, we would need to know how fast is the source moving. So let's assume that source is moving with speed and we will call this US. Okay, U stands for speed and S stands for source. And in this particular situation, our receiver will be stationary. So stationary receiver, right? The receiver is stationary. We would also need to know the frequency, right? So source frequency is something we need to know. So source frequency is going to be, let's call it Fs. All right. So if the source frequency is Fs, and then we would also need to know the speed of sound. So let's say speed of, in this case, we'll generalize it and say speed of wave. So speed of wave is just going to be v. So if the speed of the wave is v and the frequency is Fs and the wavelength, the stationary wavelength is lambda, then we all know that v is equal to lambda times Fs. Okay, the other thing that one can also talk about is the time period, right? So time period of these oscillations. So time period of the wave is for the stationary uh, thing. So when the source is stationary, then that time period Ts is equal to 1 over Fs. Okay, so that's the idea. And then once we have a receiver or an observer, so let's call that a receiver. So the receiver will receive frequency. The frequency received will be Fr, and the wavelength received, we will call that lambda r. So wavelength is lambda r. Now you can see that if depending on whether the receiver is up here or down there, this lambda r is going to be different. Particularly, lambda r is going to be lambda f in front and lambda b behind. Now let's discuss how to express lambda f and lambda b in terms of all the known parameters in this problem. So first of all, if you think about lambda f, this is the reduced wavelength in front of the source for a moving source, right? So it's the lambda f is this wavelength over here. So how do we figure that out? Well, if the source wasn't moving, this would have been lambda, but since the source is moving, the wavelength is reduced, so we have a negative sign. And how much is it reduced by? Well, it's the amount that the source moved within one period. So it's speed of the source, right, us, multiplied by the time period ts, us times ts. So that's how much the source moved, and hence that's how much lambda or the wavelength got decreased. Now, similarly, we can clearly write lambda b is equal to lambda plus us times ts. Okay, so either of these formulae we can now simplify a little bit because we know that ts is equal to 1 over fs. So we can plug that in and we get lambda minus US over Fs. And in the second case, we get lambda plus US over Fs. Okay, we can now go back to our other formula, V equals lambda times Fs, which tells us that now we want to express Fs in terms of V and lambda, right? So V is the speed of sound and lambda is the original wavelength. So Fs equals V divided by lambda. And so we can use this and plug it into our equations. And so what we get is this equals lambda minus US divided by V over lambda. And in the second case, we get lambda plus US divided by V over lambda. All right, we can simplify this further. This lambda in the denominator, because it's in the denominator of the denominator, we can just, bring it up to the numerator, and what we would get would look like lambda minus lambda times US over V. And in the second case, we'll get lambda plus lambda times US over V. And we can keep doing the algebra. I'll go to the second line. So lambda F is equal to now lambda minus lambda US over V. So this, I can pull the lambda out and I get 1 minus US over V. And I can go further and write this as lambda times V minus US divided by V. And so that's the case for the observer that is facing the source and the source is moving toward the observer. If the source was moving away from the observer, so that's the case where we have lambda b. So for lambda b, that is equal to lambda plus lambda US over V. And I can do the same algebra, lambda, I can pull lambda out, factor it out, 1 plus US over V. And so this equals lambda V plus US divided by V. Okay, so that's for lambda, but remember lambda and frequency are inversely related, right? So one can actually write the relationship over here when we had Fr and lambda r. We know that Fr times lambda r is equal to V, because the speed of sound in any of these cases is exactly the same, or the speed of the wave in this case. Right? It's always the same. So then we can talk about a frequency in front. So FF, that's going to be equal to V divided by lambda F. And if I do that using this equation, then I will get V over lambda multiplied by V over V minus US. And I'm simply just taking this quantity over here and putting it in the denominator. And so once that's in the denominator and you want to bring it up to the numerator, you'd have to flip the ratio, so you get V over V minus US. And now note that V over lambda is our favorite relationship over here, right? V over lambda is just Fs, that's the source frequency. So this is equal to Fs times V over V minus US. Okay, and finally, we can also come up with FB. So that's equal to V over lambda B. And you can do the same algebra. This will become V over lambda multiplied by V divided by V plus US here. So that's equal to Fs times V over V plus US. So essentially, we have worked out the frequency and wavelength for the situation where the source is moving, but the receiver or observer is stationary. So we'll call receiver stationary. And the first case, case 1, is source moving toward receiver. So in this case, the frequency F, the new frequency, Fr, the received frequency, is equal to F source multiplied by V divided by V minus US, where as usual, V is the speed of the wave and US is the speed of the source. And then number 2 is the situation where source is moving away, source moving away from receiver. So in that case, FR, the received frequency, is equal to Fs multiplied by V divided by V plus US, right? So as you can tell here, V minus US is smaller than V, so this is actually larger than Fs. Yeah, so when the source is moving toward the receiver, the sound frequency increases. When the source is moving away from the receiver, with a similar argument will tell you that this is actually less than Fs. So the sound frequency decreases. Now we will talk about Doppler effect for a stationary source but a moving receiver. So here in this picture, there's a source at the middle over here. So there are waves of sound, or just waves that are coming out from the source, and they're moving radially outward. So that's the circles, or in 3 dimensions, these would be just spheres, are really the wave fronts that are coming out. And then there's a receiver over here somewhere, and the receiver is moving. The receiver could either be moving toward the source along that direction or away from the source. And depending on which direction the receiver is moving, the frequency of sound or wave received by the receiver will be different from the original frequency that the source is putting out. So how does that work? Well, if you think about it, when the receiver is moving toward the source, although the source is putting out waves at equal intervals, once the receiver receives the first pulse, for him or her to receive the second one, it takes a little less time because the receiver by that time has already moved forward toward the source a little bit. And in the other situation where the receiver is moving away, it takes slightly more time for the receiver to get the next pulse. So that's why when the receiver receives the frequency, it seems like it's either shortened or lengthened. So let's actually work this out. So what we're going to do is we're going to assume that the speed of the receiver, so speed of receiver, will be UR, and speed of sound, as it is before, speed of sound is V. Speed of sound, or we can also call it just the speed of wave, is V. Okay, and so because of this, if we now know, let's say, the frequency, so frequency of wave, so let's call the frequency of wave Fs. This is the source frequency, right? Frequency wave at the source, not the one that is received by the receiver. So frequency of wave is Fs, which means that the time period is just Ts is equal to 1 over Fs, just like before. Okay. So now, of course, the receiver sees the time period as slightly different. So receiver time period, we will call that, let's say, TR. And then the receiver frequency then, that frequency is just going to be inverse of the time period. So the frequency received FR is equal to 1 over TR. So now let's think about what goes on during this time TR. So during the time TR, right, the wave is moving from the source toward the receiver, and the receiver is moving from the original position where the receiver received the first wave toward the source. And so we can say that V, which is the source speed for the sound of the wave, so V multiplied by Ts, this is the total distance from the source to the receiver's original position, right? So that distance is v times ts. So that must be equal to the sum total of the distance traveled by the next pulse and the receiver. So the receiver within time tr travels or actually the sound travels v times tr, and the receiver travels ur times tr, right? So the sum total of these two distances, this is how much receiver travels, and this is how much sound or the wave travels in time tr. And these sum total of these two have to be equal to the total distance that the stationary source wave would have traveled to reach the original receiver, right? Okay, so now we can use the relationship between time period and frequency. So first of all, we can simplify this a little bit further. We can write this as v times ts is equal to, let's factor out the tr times v plus ur. All right, so now we can invert this relationship and get 1 over ts is equal to 1 over tr multiplied by v over v plus ur. Okay, but 1 over ts, this quantity here, that is just fs, and 1 over tr, that's just fr. So that also tells us that fr is equal to fs times v plus ur divided by v. Okay, so that's how the frequency changes if the receiver is moving toward the source. Now, if the receiver and the sound wave are moving in the same direction, meaning if the receiver is moving away from the source like that, so that the sound wave is also moving in the same direction as the receiver, then this relationship over here changes a little bit. So in that case, we will have VTS must be equal to VTR minus URTR. So essentially, the idea is that the total distance covered by the sound is something longer, and then the receiver moves that much. So this distance over here is URTR, that is V. This outward distance here is VTR. So now if you subtract VTR from URTR, that's when you get VTS, right? So again, one can simplify this and write this as VTS is equal to V minus URTR. And once again, we can do the algebra. 1 over TS is equal to 1 over TR. 1 over TR times V divided by V minus UR. And we can use Fs for 1 over Ts. So this 1 over Ts over here, that is just equal to Fs. 1 over Tr similarly is Fr. So I can get Fr is equal to Fs multiplied by V minus Ur over V. Okay, so we get two formulae. This one is when the second one is receiver moving away from source, and this is receiver toward source. All right, so now let me just briefly summarize as to the results that we found. So in this scenario, just like in the previous scenario, we had two situations. The receiver was stationary, but the source was moving. This time what we are going to do is source stationary. So with a stationary source, again, we have two conditions. The first one is receiver moving toward source. So when the receiver is moving toward the source, that's when we get F receiver is equal to F source multiplied by V speed of the source or speed of the wave plus UR speed of the receiver divided by v, which is the speed of the wave. So that's one case, and the second case is receiver moving away from source. So receiver is moving away from source, which means Fr is equal to Fs multiplied by V minus Ur divided by V. All right. Okay, so far we have worked out the Doppler effect formulae for receiver stationary, source moving toward or away from receiver, and then separately source stationary, receiver moving toward or away from the source. Notice one thing though, that we can set up a convention and then make these formulae slightly easier. So let's say that this is my source and this is my receiver, right? If the source, let's take the receiver stationary situation. So this is my receiver, let's call it R. This is my source S. So if the source is moving toward the receiver, so let's say the source is moving toward the receiver. In this situation, I will call my source speed positive. So US is plus, which means that as soon as my source starts moving away from the receiver, so if the source is moving away from the receiver, then my US, the U source, is now negative, right? US is minus. So with that convention, then we can just come up with a single formula to represent both of these. So, and that's going to be FR is equal to FS times V over V minus US. And so when US is positive, of course, this formula is just exactly how it is. But when US is negative, then this V minus US just becomes a V plus US, which represents the source moving away from the receiver. Okay, so our convention will be when the source is moving toward the receiver, the source speed is positive. We can do a similar thing for when the source is stationary, but the receiver is moving. So in this case, notice that if I say that my receiver's motion toward the source, when the receiver is moving toward the source, we will consider that as my UR being positive. Okay, so when receiver is moving toward the source, UR is positive. When the receiver is moving away from the source, UR is negative. So with that convention, then we can come up with a more general formula for the second part. So that becomes FR is equal to FS multiplied by V plus UR divided by V. Meaning when UR is positive, that is the receiver is moving toward the source, then you use the plus sign over here with UR a positive quantity. But then if you are interested in the case where the receiver is moving away from the source, all you have to do is just use a negative value for UR and you get V minus UR over V, right? Okay, so now we're going to put these two together, okay? So we're going to put these two together, meaning that both the receiver and the source are moving. Okay, so receiver moving with speed UR, and it's moving toward the source so that it is positive. In our convention, toward source is a positive speed, toward source. And then we have source moving with speed, and this is US, that's the source speed, and this is also moving toward receiver. So since it's moving toward receiver, this is also positive by our convention, right? When receiver is moving toward source, that's positive. When source is moving toward receiver, that's positive. So both of these cases are plus cases. So we can just put together these two formulae and we get FR is equal to FS multiplied by V plus UR divided by V minus US. And that's our master formula for Doppler effect. See that in each of these cases, If we now take the limiting situation, so for instance, take the limiting situation where the receiver is moving with speed 0, right? So that's if the receiver is moving with speed 0, that's stationary receiver. That means UR vanishes. UR equals 0. So if UR is equal to 0, you get back this FR equals Fs times V over V minus US. And similarly, when US is equal to 0, that is the source is not moving, the source is stationary, you get back FR equals Fs times V plus UR over V, right? So this is going to be our important Doppler effect formula for frequency for new frequency. And of course, one can also find the change in frequency, right? So the change in frequency is often something that may be asked. So in that case, you just have to figure out the difference between the original frequency Fs and so delta F will be equal to Fr minus Fs. So this is going to be Fr minus Fs, because Fs is the initial before the change, before the Doppler shift, and this is the Doppler shifted. Fr is the Doppler shifted frequency. Okay, so I think that is essentially enough for Doppler effect formulae. We can now use these formulae to solve problems where some of these quantities such as Fs, V, and UR are given, and maybe US is given, and you're expected to find FR. Or one can switch the problem around and give you Fs, V, UR, and FR, and expect you to find US or some combination of such problems. All right, so I'm going to stop over here. I hope you enjoyed this video. Thank you very much.